achieve MPPT in panel orientation. I am Sean Reams, the team leader, and our project supervisor is Dr. Jabber. My team members are Nathan Miller, Michael Mayhall, Ronnie McCoy, Jonathan Knight, and Blake Yarborough. Our agenda today is we're going to give you a little solar panel background, along with some MPPT background, show you a system block diagram, give you some validation info, along with some impacts and concerns. The deliverables we want to have are a self-sustained power system, fast electromechanical power tracking, and accurate power tracking, and provide more output power than just an immobile panel. Some of the clients that can benefit from our project are small to large corporations, recreational vehicles, planetary navigation with robots, residential communities, disaster relief, and military use. And now I'll hand it off to Nathan Miller to give you some solar panel background.
We're going to first start off with how solar cells work, also known as photovoltaic cells. Photovoltaics is the conversion of light into electricity. It uses a property known as the photoelectric effect, which causes the material to absorb photons of light and release electrons. When these electrons are captured, an electric current will result. When we start looking at solar panels, we notice that there's some variables we can control and some we can't. Some of the ones we can is, of course, molecular makeup, temperature, weather, and the solar irradiance, which is the specific amount of solar energy at a certain point, certain period. Things we can control or within the scope of our project are panel orientation. We can regulate the voltage and current, and we can minimize the amount of power our system uses. Now to explain MPPT, Michael Mayhall.
All right, our goal is to achieve maximum power conversion through panel orientation. To do this, we first have to understand how panel orientation affects power conversion. A lot of lab tests have been done to show that a panel will provide maximum power conversion when it is positioned perpendicular to the sun's solar rays. As this graph shows, you tend to lose power by a factor of cosine theta as you shift between plus and minus degrees of that position. Our goal is to find that position where our plane of our solar panel is in perpendicular to the sun's solar rays. To do this, we first have to be able to track the sun and know where its brightest rays are at all times. And there are two methods that are useful to us to do so. One is the sensor tracking method. This will compare 2 points and know which one of the two is the brightest point to be able to know that that is the direction of the sun. The other method is the sweeping maximum power point tracking method. This is more of a brute force type method, and it will find all power values within a given range to know which one of those is the brightest spot. The sensor tracking method is the fastest of the two. The sweeping tracking method is the most accurate of the two. Here is a flow chart as well as a physical diagram of the sensor tracking method. As you can see, the microcontroller will receive inputs from two sensors and compare the two. When one sensor is sending a larger input to the microcontroller, it will rotate our motors in the direction of that sensor. When the opposite sensor is sending in a larger signal, it will rotate the motors in the opposite direction towards that sensor. Eventually, both sensors will send approximately the same signal, and we will be able to cut off power to our motors, and we should be very close to our maximum power plane. And we can use our sweeping MPPT method. As you can see here is a flow chart and a physical diagram of how that works. We can sweep our board within a given range, and while doing so, our microcontroller will record all values of power that it reads in. At that point, after it's finished with the sweep, we can compare all the values that we have read in and know which one of those values was the highest. At that point, our microcontroller can index our motors back to that position. And at this point, we should be at our maximum power point possible. This is a system block diagram that shows how our subsystems will be integrated to provide a fully functional system. You can see here that our solar panel will provide charge to our battery by the means of a DC to DC converter and a charge controller. At this point, our battery can then supply power to our motors for panel orientation, as well as our microcontroller for processing. We will also use some sensors, some light sensors and current sensors for both of our power tracking methods. To do this and make our system more manageable, we're going to break it down into 3 subsystems. We'll have our computing subsystem, our power management subsystem, as well as our electromechanical subsystem. On our computing team, we'll have Blake Yarborough and Jonathan Knight. They will handle all sensors, inputs, coding, anything related to tracking the sun. And for our power management system, will be Nathan Miller and Ronnie McCoy. And they will handle storing all the power that we have converted, as well as distributing this power to the rest of our components that we need. On our electromechanical team will be Sean Reams and myself, and we will handle all the electrical and mechanical hardware involved in orientating our panel in the correct position. First is our frame, and this is very important to our design, as this will determine and give the support to where our panel will eventually reside as it does its maximum power conversion. It needs to provide a few things, some of which include being able to provide 2 directions and degrees of freedom. One is a horizontal degree of freedom in a rotational direction. The other is a vertical rotational degree of freedom. It will also need to be lightweight so that it can be mobile, as well as sturdy to withstand environmental conditions because it will be outside. It also needs to provide room on the frame itself for any other components and parts necessary for tracking the sun and converting maximum power. This is a preliminary design for a frame. As you can see, it provides 2 degrees of freedom, a horizontal rotational degree of freedom by rotating the base as it rests on a bearing, as well as a vertical rotational degree of freedom as it rotates the shaft upon which the solar panel will sit. We can expand on this frame design by adding wheels to the base of the frame. This will help to distribute weight out across the base of the frame, as well as provide support for our frame and any components resting on it. This should make it easier for our motors to rotate the frame. And now to talk about those motors, here's Sean Reeves.
In the scope of our system, we were looking at DC motors to achieve our self-sustaining system, and first on the list would be a brushed DC motor. Brushed DC motors are nice because they don't require an elaborate controller to control them, but there are other options outside to control them. But unfortunately, brushed DC motors also have the highest maintenance of the motors that I'm about to explain. Brushless DC motors overcome the wears by implementing commutation with an electronic control. But they also require some electronics for speed and position. Next on the list would be stepper motors. Stepper motors are a good motor to use because each step is a certain degree, and these steps are achieved with a low % error, and the errors are non-cumulative across the whole span. But they are short of, they cannot run at high speeds. Servo motors, on the other hand, would be ideal for our project. They run at high speeds and high torques, but require elaborate control systems and feedback loops to achieve the control that you need. But that's also a plus, where it gives the user more availability on how to control them. Now I'll pass it off to Ronnie to give us some battery information.
The battery we use will be a rechargeable battery that will receive constant charge from the solar panel and we use this charge to power our circuit. There are 3 types of batteries we researched when considering which one best suits our circuit's needs. We have the flooded battery, the gel battery, and the absorbed glass mat battery, also known as the AGM battery. A major con we noticed about the flooded battery is that it disperses fumes which can become corrosion hazard to our circuit. This is economically a disadvantage to us because corrosion damage costs us time as well as money to find replacement parts for our circuit. A major pro for the gel battery is that it's tolerant of high and low temperatures, which means that it will not freeze when working in cold environments and will not overheat when working in hot environments. And the AGM battery, unlike the flooded battery, does not leak or crack and will not corrode. However, it is not tolerant of high and low temperatures, which means that the capacity is decreased a lot when in low temperatures, and it has a high chance of overheating in high temperatures. Because the solar panel is constantly charging the battery, we will need something to regulate this charge. A battery is very particular about how it likes to be charged. It doesn't want to be overcharged or undercharged. The charge controller monitors the device of charging to a certain point where it's fully charged, and then cuts the electrical flow of the battery in the circuit so it can continue to work properly. The solar panel depends on the sun for its charging. The solar panel will output at varying voltages throughout the day, as well as the seasons, due to cloudy days and daylight saving time. Therefore, we need a DC-DC converter to output at constant voltage from this solar panel. Say the solar panel was outputting 12 volts, but we need to output 13. We'll use a boost converter to get that output voltage that we desire. Or if it's outputting 12 and we need 10, we'll use a buck converter to output the voltage that we desire. I'll now give the floor to Jonathan Knight so he can talk to you all about systems and implementation.
As we mentioned, we're using two methods to position the solar panel. First, going to use sensors to determine the position of the sun. The sensors that we're using fall under the category of photosensors because they are used to detect the presence of visible light. We will need to build a module to implement these sensors. And this module will be attached to either the panel or the frame in a way such that the sensors will be facing the same direction as the panel. This way we know that once all sensors are receiving direct light, the panel will also be receiving direct light. The sensor module will need to have a wall on it that will separate multiple sensors. This wall will create a shadow if the sensors are not getting direct light. This will allow us to use the sensors as a digital mode in a way such that the sensor is considered off if the sensor is not receiving direct light because of the shadow from the wall. And if the sensor is receiving light, it's considered on. As you can see in this example, the sensor on the left is in the shadow created by the wall, and the sensor on the right is in the light. Therefore, the module and panel will tilt towards the sun, and that way all sensors will be receiving light as well as the panel itself. Two photosensor options are light-dependent resistors as well as photodiodes. A light-dependent resistor is a resistor whose resistance value varies depending on the amount of light shining upon it. It will have a much lower resistance in the light and a much higher resistance than the dark. The pro for using a light-dependent resistor is that it's much cheaper than a photodiode. However, they are a little inconsistent. For example, you could have two identical parts. One of them could read possibly 20 kiloohms in the light, while the other reads 30 kiloohms under the same lighting conditions. A photodiode, on the other hand, produces a current that is proportional to the light intensity upon it. The greater the light, the greater the current that will flow. The photodiode is a little more expensive than the light-dependent resistors are. However, they are more consistent than the LDRs. And to control the system, we will need to use a microcontroller, and Blake will discuss the microcontroller options.
Looking at a microcontroller, there are 4 factors that are going to play into which microcontroller board that we want to decide to buy. First of these 4 is memory. Out of these 3, EEPROM memory is the most important for us. EEPROM memory is electronically erasable, programmable, read-only memory. This is very important for our system, in the sense that if our microcontroller board were to go under operating voltage, it would be able to retain the data that it possesses, i.e. our code. This code will be, we'll have to implement the flow charts that you can see on slides 10 and 11 that Michael went over previously. Next is I/O, being able to support the LDRs or like photo sensors that Jonathan was talking about. We'll have to have at least 6 digital inputs, and also supporting Sean's motors will have to have at least 2 digital outputs, in the sense that if we used